This is the second lecture for digital signal processing KEC 503, and the topic that I have taken is IIR digital Chebyshev filter design. Okay, so I am Dr. Amit Garg, associate professor in EC department of AKGEC. So let us start with the IIR digital Chebyshev filter design. So before going this IIR digital filter design, we are having two types of filters basically for which we have to design the filters. First is Butterworth filter and second one is the Chebyshev filter. So I am taking this topic as Chebyshev filter designing. Okay. So if we'll talk about the Chebyshev filter design and Butterworth filter design, both comes under the common category that are all pole filters. So you can say all pole filters are, you can describe by this transfer function HAS equals to A dash upon PS, where A dash is the polynomial of degree n and A is a constant. So most important low pass filters of this type are Butterworth and Chebyshev filters, and these filters are often realized in cascade form, so that transfer function is usually written in the form. Okay, so this A dash upon PS is basically the all pole type of transfer function where polynomial of S is only in denominator and A is the constant. Means whenever we will talk about all pole transfer function, then only poles will be there, there are no zeros. So that's why this part is the constant. So this is the very general transfer function. If we will see, this is the very general transfer function. Now if we will see specifically, we can write down the analog filter transfer function like these two expressions by equation 2 and equation 3. Okay. So this is your equation 2 and this is your equation 3. So equation 2 is HAS equals to multiplication K equals to 1 to n by 2 BK ohm C square upon S square plus BK ohm CS plus CK ohm C square. So this formula is used when we are having the values of n as even values like 2, 4, 6, 8, 10 up to so on, and these are the expressions when the filter order is 1, 3, 5, 7, or you can say filter order is n. Filter order is odd. So for n equals to 1, we can see if we will put over here, then this value will become 1 to 0 and only this part will be taken. And for n equals to 2, if we will write n equals to 2, so then this is k equals to 1 to 1. It means the values are B1 ohm C square upon S square plus B1 ohm CS plus C1 ohm C square. So this is the general transfer function. So now for obtaining the analog filter transfer function, we have to put the values of capital B1, small b1 and small c1 here in this transfer function. So you can say for n equals to 2, we have to calculate the value of capital B1, small b1 and small c1, and here the value is you can see the value is B0 ohm C upon S plus C0 ohm C for n equals to 1, and for n equals to 3, if we will see, this value will become from 1 to k equals to 1 to 1. It means the value is B1 ohm C square upon S square plus B1 ohm CS plus C1 ohm C square. Now we have seen there are three coefficients based on which you can say this transfer function is dependent. One is capital BK, small bk, small ck. Another thing, there is cutoff frequency also. So if we know all these values, then we can obtain the transfer function for a particular type of filter order. Okay. Now if we will see the Butterworth case, then in that case these coefficients are calculated as per Butterworth designing equation, and if we will talk about the Chebyshev filter design, in that case these coefficients are calculated as per Chebyshev filter designing. Okay. We will calculate accordingly. So now I have included only Chebyshev filter designing in this particular lecture. So let us go through that. So Chebyshev filters. So the Chebyshev low pass filter has a magnitude response that can be defined as Hj omega equals to A upon 1 plus epsilon square Cn square omega by omega C whole power 0.5. So this is the expression, or this is the magnitude response of Chebyshev low pass filter, where A is the filter gain, epsilon is the constant, and omega C is the 3 dB cutoff frequency. Okay. So now what is this Cn omega by omega C? So this is Cnx, or you can say this is called as Chebyshev polynomial of the first degree of nth order. So the value of this Chebyshev polynomial is dependent upon this value x, and according to this expression, for all values wherein mod x is less than equal to 1, the formula for Cnx that we will use for calculating the Chebyshev polynomial is cos of n cos inverse x, cos of n cos inverse x, when mod x is less than equal to 1. And what happened if the value of x is greater than 1, or you can say for mod x greater than 1, this value will become cos of n cos hyperbolic inverse x, cos of n cos hyperbolic inverse x, and this can be written as cos of, you can also write, this is the complicated formula, so you can also write this expression by cos hyperbolic of n log x plus under root x square minus 1. So, you can use either for mod x greater than 1, you can use either cos of n cos hyperbolic inverse or cos of hyperbolic n log x plus under root x square minus 1. Okay. So, this is the expression by which we can calculate the Chebyshev polynomial of first kind of nth order. Okay. So, now we will see this is the magnitude response of a Chebyshev low pass filter. If we will see the ideal filter response in case of low pass filter, this is the ideal filter response. Okay, this is the ideal filter response. But practical response which we will get through a Chebyshev filter is like this. So, you can see we are having ripples here. These are the ripples that we are getting in the pass band, and you can say this is the stop band. So, you can see here the ripples are found in the pass band and stop band is flat, and stop band is flat. Okay. So, in case of Chebyshev filter, you can see the ripples are in the pass band or equiripple pass band you are obtaining here, and you can say maximally flat stop band is there. If we will compare it with the Butterworth filter, then we have seen that in the case of Butterworth filter, we are having maximally flat pass band as well as maximally flat stop band. But here at the expense of some ripples here, we are achieving better magnitude response for the same filter order as compared to Butterworth filter. Now, we can see here again, if we will increase the order of the filter, then what happened, this response will approach in this direction, or you can say this will approach in this direction, or you can say the overall response while increasing the filter order n will approach towards the ideal filter response. Okay. So, this is the magnitude response of the Chebyshev filter. It has equiripple pass band and maximally flat stop band. It can be seen that by increasing the filter order n, the Chebyshev response approximates the ideal response. Another thing is that we are talking about the magnitude response. What about the phase response? The phase response of the Chebyshev filter is more non-linear than the Butterworth filter for a given filter length n. So, you can say if we are having a choice that which filter we have to use, Butterworth and Chebyshev, and you can say in Chebyshev filter we are having better magnitude response as compared to the Butterworth filter. But here we can see if we will talk about the phase response, then phase response for a given filter order n is more non-linear in case of Chebyshev filter as compared to the Butterworth filter. Okay. So, now how we are again we will see that how we are getting this type of response. So, you can see that the value of this Hj omega magnitude is dependent upon the factor Cn square ohm by ohm c. Okay. So, if ohm by ohm c value, so you can see when cutoff frequency omega c will be less than or will be greater than omega, then in that case this factor will be less than 1. So, if this factor will be less than 1, then the Chebyshev polynomial will be less than 1, then we will use this formula for calculating the value of Chebyshev polynomial. Okay. So, we can see till that omega is less than omega c, means omega c is the cutoff frequency. So, in this region we can see the value is basically this almost constant value within the interval delta 1 to a, and as soon as this omega c will be less than omega, then what happened, this value of x will be greater than 1, and we have to use this formula. Okay. So, according to this formula, as the value of x is greater than 1 and as you are moving towards x greater than 1, then this value is, you can say the value of this function we will get is you can say that is monotonically decreasing. Okay. So, that is why we are getting this type of response. So, here we are getting this response and here we are getting this response. Okay. Now, so as the value of n increases, it becomes more difficult to calculate the polynomial expression for Cnx. So, we have seen the formula for Cnx according to these expressions. Now, we can calculate the value of as the value of n, it becomes more difficult to calculate polynomial expression of Cnx. So what happened? Let us suppose if we want to calculate the value of C0x. So C0x will be 1, C1x will be equal to x, and C2x, if you want to calculate the value of C2x. Okay, so how we will calculate the value of C2x? From here, this will become, if x is less than 1, then this is cos of 2 cos inverse x, cos of 2 cos inverse x. We are taking n equals to 2. Okay, so let us suppose cos inverse x will be equal to theta. So x equals to cos theta. Okay, so C2x will be equal to cos of 2 theta. Cos 2 theta can be written as 2 cos square theta minus 1. So that will be equal to 2x square minus 1. 2x square minus 1. Okay. So C naught x equals to 1, C1x equals to x, C2x equals to 2x square minus 1. And C3x, how you will calculate C3x? Cos of 3 theta, which you can write as 4 cos cube theta minus 1. Oh sorry, 4 cos cube theta minus 3 sin theta. So accordingly you can calculate the value of this 4x cube minus 3x, or this for C4x it will be difficult to calculate according to this expression. So how we can calculate? We can calculate this using this recursion formula. Like if you want to calculate C3x, then C3x will be equal to 2x C2x minus C1x. So this will become 2x C2x is, we have calculated 2x square minus 1, and C1x is x. So you can calculate this is 4x cube minus 3x. For C4x, if you will calculate C4x, then C4x will be equal to 2x C3x minus C2x. So accordingly you can calculate the value using this recursion formula for any value of Cnx. Okay. So based on this, the properties of Chebyshev polynomial can be defined like this. So these are the properties of only Cnx or the Chebyshev polynomial, not the complete Chebyshev low pass filter. So these properties says that mod of Cnx will be less than equal to 1 for all mod x less than equal to 1, and Cn1 equals to 1 for all n, means whatever may be the value of n, it is independent, if it will be 1 if the x value is 1, means ohm equals to ohm c. We are talking about the condition where ohm equals to ohm c. So in that case Cn1 will be 1 for all n, means you will take any value of n, the value will become 1, and all the roots of the polynomial Cnx occur in the interval minus 1 to 1. So mod of Cnx increases monotonically for mod x greater than 1. This we have seen here, like if this value will be monotonically increasing, so in the denominator the value will be monotonically increasing, so this overall value will become decreasing, you can say. Okay, so these are the properties of the Chebyshev polynomial. So this is how we have obtained the Chebyshev polynomial. Here x equals to ohm by ohm c, or you can also call it omega by omega c. This is actually large omega by large omega c. If we are taking omega c as the normalized frequency, then this value will become 1. It means you can say simply x will become omega. So now we are taking two cases, when omega or x is lying between 0 to 1, and another case is when omega will be lying between greater than 1. Okay. So this is the case that I have already discussed previously. So you can calculate the value of C0 omega, that will be 1. For C1 omega, that will be omega. For C2 omega, that will be 2 omega square minus 1. For C3 omega, that will be equals to 4 omega cube minus this is 3 omega minus 3 omega, and C4 omega will be equal to 8 omega to the power 4 minus 8 omega square plus 1. Okay. Now we will see the case where omega and omega is nothing but x, and this will be greater than equal to 1. So the Chebyshev polynomial Cnx for this region is given by Cn omega will be cos of hyperbolic n cos hyperbolic inverse gamma. Okay. So you can write it like cos hyperbolic on n cos hyperbolic inverse gamma, Now let us suppose we have taken this cos hyperbolic inverse gamma equal to y. So this you can write as gamma equals to cos hyperbolic y. Cos hyperbolic y you can write as e to the power y plus e to the power minus y upon 2. Okay. Now we are assuming that cos hyperbolic equals to e to the power y upon 2. E to the power minus y, let us suppose the value of y is very high. For y very far greater than 1, it means this value e to the power minus y is very less, so we can neglect it. So we have assumed at e to the power y equals to 2 omega. This is just we are taking for the sake of simplicity. Now we can take the natural logarithmic on both sides. So y equals to log of 2 omega. Okay, so log of 2 omega, and this will be equal to cos of hyperbolic inverse omega. So therefore Cn omega will be cos of hyperbolic n. Cos hyperbolic inverse equals to log of 2 omega, and this we can write as cos hyperbolic log of 2 omega to the power n, and so cos of hyperbolic, this we can write it like this, like cos hyperbolic y equals to e to the power y plus e to the power minus y by 2. So similarly cos of hyperbolic of log 2 omega by n is e to the power ln 2 omega to the power n plus e to the power minus log 2 omega to the power n. Again for gamma, or again for omega, or omega far greater than 1, we will neglect this term. So the term will be e to the power log 2 omega to the power n upon 2. So you can also write it as e to the power log n 1 by 2 omega to the power n. So this is the value of Cn omega. Now we will calculate the value of C naught omega. So C naught omega will be equal to, we'll put n equals to 0. So this is equal to 1 by 2. Now C1 omega, we will get the value omega. C2 omega is 2 omega square. C3 omega will be equal to 4 omega cube. Okay, so these are the values that we are getting for Cn omega. Okay, so this is how we will calculate the value of Chebyshev polynomial in the case when the value of omega is less than 1 and the value of omega when omega greater than 1, or you can say also the value of x equals to omega. So you can also call it for value of x. Okay, now we will design the we will see the designing equation for Chebyshev filter. Okay, so we know in case of low pass filter, this is the low pass band edge frequency, pass band edge frequency, pass band edge frequency, pass band edge frequency, and this is nothing but stop band edge frequency. Okay, so you can see here this is the magnitude delta 1, means the pass band magnitude is lying between delta 1 and 1, and delta 1 value is the, you can see delta 1 value is this value. So means the magnitude in the pass band is varying between delta 1 and 1. Okay, and the value of stop band, you can see the value is between 0 and delta 2. So the between 0 and delta 2, this is the pass, this is the stop band specification, because omega 2 is stop band edge frequency. So this you can also write it like, if there is a confusion, you can also write it like this. So mod of h e to the power j omega less than delta 2. Okay, so the corresponding analog magnitude response is to obtain in the design filter if a equals to 1. So we are assuming that the value of a is equal to 1, and what we will do, basically we are squaring on both sides. So delta 1 square is less than equal to mod of h e to the power j omega whole square is less than equal to 1. Now what is the value of mod of h e to the power j omega? If we will see, this is nothing but 1 upon under root 1 plus epsilon square Cn square ohm by ohm c. So when you will square it, then this under root will be gone. So you will get delta 1 square is less than equal to 1 upon 1 plus epsilon square Cn square ohm by ohm c. Okay, so but we are taking it for pass band. So we are taking it pass band. So in case of pass band, the pass band edge frequency is omega 1. So that's why we have written as 1 upon 1 plus epsilon square C1 Cn and omega 1 by omega c. And similarly here, now the pass band edge frequency is omega 2. So we can call it, we can write it 1 upon 1 plus epsilon square Cn square omega 2 by omega c is less than delta 2 square. Now for the simplicity in the design, what we are assuming? We are assuming that this omega c will be equal to omega 1. So when omega c will be omega 1, then this will become Cn omega c by omega c, or Cn1, that will be equal to 1. Okay, so we can write this equation 4 as delta 1 square is less than equal to 1 upon 1 plus epsilon square, because when omega 1 equals to omega c, then this value will become 1 and Cn1 is equal to 1. So here we are getting the relation delta 1 square equal to 1 is less than equal to 1 upon 1 plus epsilon square. So for calculating the value, we are taking the equality sign, 1 upon 1 plus epsilon square. So from here you can calculate the value of epsilon with this expression, because you have given this value of delta 1 square. Okay. Again we are assuming that omega c equals to omega 1. What is omega 1? Omega 1 is the passband H frequency. So here we are assuming, in case of Chebyshev filter designing, that the passband H frequency is nothing but the cutoff frequency. Okay, so passband H frequency is nothing but the cutoff frequency. This is just we have taken for the you can say as an approximation for easy out the calculation. Okay. So from here in this expression we can calculate the value of epsilon, and the value of epsilon is equal to 1 upon delta 1 square minus 1 to the power 0.5. The order of the Butterworth filter n can be determined from equation 5. From this we can calculate the order of the filter. So assuming omega c equals to omega 1, now Cn omega 2 by omega 1. Okay, so this we are calculating Cn omega 2 by omega 1, because omega c equals to omega 1. So if you will calculate this, we will get, according to this expression, if we will take the equality sign, or we are taking equality sign or not, doesn't make any difference. So this expression will become Cn omega 2 by omega 1. We are assuming that omega c equals to omega 1. This is written over here. So Cn omega 2 by omega 1 is greater than equal to 1 upon epsilon, 1 upon delta 1 square to the power 0.5. Okay. Now you can write the expressions, because you know that omega 2 is greater than omega 1. So this value, let us suppose x, so x will be greater than 1. So in that case the hyperbolic inverse definition will be work. So cos hyperbolic and cos hyperbolic inverse omega 2 by omega 1 is far greater than 1 upon epsilon, 1 upon delta 1 square to the power 0.5. So n will be greater than equal to cos hyperbolic inverse. So if we will take n, then this will become, we will take the cos hyperbolic inverse. So 1 upon epsilon, 1 upon delta 1 square to the power minus 1 to the power 0.5 upon cos hyperbolic inverse omega 2 by omega 1. So this is the order. So this is the formula for calculating the order, and this is the epsilon, and these are the formulas for the designing of Chebyshev filter. So I have already discussed that there are three coefficients like bk, small ck, and capital Bk. So the formulas for those are given here. Bk equals to 2yn sin 2k minus 1 pi by 2n, and ck is yn square plus cos square 2k minus 1 pi by 2n. And important thing is that C0 will be equal to yn, whatever the value of yn is there. And yn is given by this formula 1 by 2, 1 upon epsilon square plus 1 to the power 0.5 plus 1 upon epsilon whole power 1 by n minus 1 upon epsilon square plus 1 to the power 0.5 plus 1 upon epsilon whole power minus 1 by n. And bk can be using this formula a upon under root 1 plus epsilon, a upon under root 1 plus epsilon equals to k equals to 1 to n by 2 bk by ck. So using this formula we can also calculate bk if ck we have calculated using this formula. So these are the designing formulas based on which we can calculate the values. Okay. Now we will see one problem, that how we will obtain how we will obtain or how we will design a digital Chebyshev filter using bilinear transformation. So this is the expression given as, so this is basically nothing but omega 1, this is omega 2, this is delta 1, this is delta 2. Okay, so these are the values. Now we will calculate, first of all we will calculate omega 2 and omega 1. So omega 1 is 2 by t tan omega 1 by 2. With this expression we can calculate the value of omega 1, and omega t is 2 by t tan omega 2 by 2. Why we are using this? Because we are designing this filter using bilinear transformation. So in this case bilinear transformation we will calculate the values of analog filter frequency from the digital filter frequency according to this expression. So after calculating the value of omega c, and the value of omega c is nothing but value of omega 1, and then we will calculate the omega 2 by omega 1, that will be equal to 3.077 9. Now we will calculate the value of epsilon using this formula. So the value of epsilon when we will calculate using this formula, it will become 1. Then we will apply the filter order formula. So that will be equal to n is greater than equal to cos hyperbolic inverse 1 upon epsilon 1 upon delta square minus 1 to the power 0.5 cos hyperbolic inverse omega 2 by omega 1. Now we will calculate. Now we will put the value of delta 2 omega 2 by omega 1 we have already calculated here 3.0779. So when we will solve this, we are getting the value of n greater than 1.669, which we can taken as 2, which we will taken as 2. Now we will put this value here. We will put this value in the determination of HS. So this formula we have already seen for even filter order. HS equals to K equals to 1 by 2 BK ohm C square upon S square plus BK ohm CS plus CK ohm C square. Okay. So now we are putting the value K equals to 1 to 1. So this value will become B1 ohm C square upon S square plus B1 ohm CS plus C1 ohm C square. Okay. Now calculate the value of Yn, because Yn is required for calculating the value of Cn. So Yn according to this expression we will calculate, and here n equals to 2. So you are saying that we are calculating the value of Y2. So Y2 means n will be 2. So you will put the value of n equals to 2 here, 1 by 2 minus 1 by 2, and you will solve that this Y2 is 0.455. Now we will calculate the coefficient value B1, where B1 is, BK is, for the expression BK we have already seen the formula, and according to this expression we require the value of small b1 and small c1 and capital B1. So small b1 is 2y2 sin 2k minus 1 pi by 2n. So यहाँ से so for this we can calculate the value of B1, that will be equal to 0.6435. This is the value. Okay, Y2 is 0.45 you will put over here, and the value of K is 1 in this case. So when we n equals to 2, so we will get the value small of B1. Then small of C1 will be equal to, we have already seen the formula yn square plus cos square 2k minus 1 pi by 2n. So when we will solve this value, Y2 will put over here, K value will become 1, so you will get the value 0.707. Now for n equals to even, now we will calculate the value of capital. In this expression the capital of B1 is required. So we will calculate the value of B1. So we will calculate this using this expression, K equals to 1 to n by 2 multiplication B capital Bk upon small ck, that will be equal to A upon 1 plus epsilon square to the power 0.5. Therefore B1 by C1 will be equal to 0.707 and B1 equals to 0.5, and the system function will become 0.5 ohm C square will be equal to, ohm C will be equal to 0.6498, omega C will be equal to 0.6498. So we will calculate omega C is nothing but omega 1. Omega 1 we have calculated here, basically this will be 0.6498. So here 0.5 multiply by 0.6498 whole square upon S square plus 0.6435 into 0.6498 times S plus 0.707 multiply by 0.6498 whole square. Okay, so this will become as HS equals to 0.2111 upon S square plus 0.4181 S plus 0.282985. Okay, so this is the transfer function that we have obtained here is for analog filter, because we are having HS which is corresponding to Chebyshev filter. Now we want HZ. Now HZ how we will obtain from HS? As per bilinear transformation, because the filter designing method is bilinear transformation. So for bilinear transformation we will put S equals to 2 by T Z minus 1 upon Z plus 1. Here I will write again 2 by T Z minus 1 upon Z plus 1, or you can also write it as 2 by T 1 minus Z to the power minus 1 upon 1 plus Z to the power minus 1. Okay, so we will put it over here 2 by T Z minus 1 upon Z plus 1, and we will put it over here 2 by T, the value of T, let us suppose we are assuming the value of T equals to 1 second. although the value is given, or if it is not given, then you can take the value of t as 1. So you will put, if you will put this value, here we have taken t equals to 1 second. So this will become 0.2111 upon 2 times z minus 1 upon z plus 1 whole square plus 0.4181. So we have just put the value of s, that is 2 by t z minus 1 upon z plus 1. Okay. So this is 0.2111, and when we will solve it, 0.2111 z plus 1 whole square, and the denominator will become 5.1347 z square minus 7.430 z minus 3.4623. So this is the value of hz. Now we can arrange it in terms of z to the power minus 1 power. So we will take z square common here, and we can take also z square from here. So we can write it like 0.0411 1 plus z to the power minus 1 whole square, and also we have divided by this term 5.1347 in numerator and denominator, so that this coefficient value will become 1. So finally the value that we will obtain is hz equals to 0.0411 1 plus z to the power minus 1 whole square 1 minus 1.4418 z to the power minus 1 plus 0.6743 z to the power minus 2. So this is basically the hz that we have obtained. Okay. So this is how we have obtained the transfer function for Chebyshev filter designing. So the references is Digital Signal Processing by S. Sullivan, third edition. Thank you.